Testing in the UK doesn't get tougher than this. The ring final circuit, or as Dave down the pub calls it, the ring main. In this video, I'm going to be showing you how to test the ring final circuit the right way and share some of our top tips to save you from the mistakes that everybody makes. Perfect if you've got a competent person scheme inspection coming up or you're approaching an endpoint assessment. So stick around, as this is one test you don't want to get wrong. So using the MFT Pro from TIS, we will switch it to continuity, zero our leads, making sure we connect the crock clips in such a way that we don't zero through the springs. We can now carry out the end-to-end resistance of the line, neutral and protective conductor. This proves we have a ring circuit but does not identify any potential issues in the ring. Once all the legs have been disconnected, we now connect the crocodile clips onto each end of the conductors, giving them a gentle squeeze to make sure a good connection is made. We start with the line conductor, which gives us a reading of 0.22 ohms. We now swap our clips over onto the neutral conductors and test again. This gave us a reading of 0.21 ohms. Moving over to the CPC, we got a reading of 0.21 ohms. We record these values as little r1, little rn and little r2, as shown here in the model form taken from BS 7671, the wiring regulations. This circuit has been wired in singles, so all the conductors are the same size, so we can expect our readings to be the same or very similar. However, if the circuit was wired in twin and earth, the CPC is smaller, so should yield a higher reading, and we can confirm this as well using calculation. The difference between a 2.5mm conductor and 1.5mm conductor is 1.67. That is 2.5 divided by 1.5. The little r1 reading is 0.22 ohms, so multiplying that by 1.67 gives us 0.37 ohms. So as mentioned earlier, this tells us we have a ring, but doesn't tell us if there's any issues in the ring like an interconnection or multiple spurs. Before we dive into carrying out the test, we are first going to work out how to calculate some expected readings to add to our numbers. So how do we do it? Let's take a little r1 and little rn from our end-to-end test earlier, and we are going to throw it in this formula, little r1 plus little rn divided by 4. This gives us a reading of 0.11 ohms, which is our expected r1 plus rn. So now we are going to confirm this by measurement. We now need to cross-connect the ring conductors. This is when we connect the line conductor from one of the ring legs to the neutral of the other legs and repeat the process with the left over legs. This is why it is so important to have your legs marked up and easily identifiable as in and out. With the cross connection made, we can now set up our MFT to measure between line and neutral.
I'm going to use the breakout lead now, but one tip for you is to remember we're testing between the line and neutral conductors, so we can get rid of that one in order to have the correct pins when we plug it into each of the socket outlets.
So connect your breakout lead into the MFT using the line and neutral probes and zero the lead. We are testing at every socket point and operating the switch to make sure it works. At socket number 1, we got a reading of 0.12 ohms. At socket number 2, we got the same reading of 0.12 ohms. At the next socket, socket number 3, we got a reading of 0.10 ohms. This is a difference of 0.2 from the last readings. This is okay, as we would expect some fluctuation in the readings, as many factors can impact resistance. But as long as the readings stay within 0.05 ohms, we can be satisfied that the connections are okay. Socket number 4 now, and the reading at this point is 0.12 ohms. We have 2 points left to go now, so it's off to socket 5, and we get a reading of 0.28.
It was all going so swimmingly well until I got to socket outlet number 5, and I've got a reading now higher than the expected calculated value. It could be a number of things. If I take the front off, I can have a look and check the terminations are nice and tight behind it. It could be on older socket outlets, so you get some pin wear where they're build up of resistance. So you go in and out a couple of times with the plug in the socket, and you can find that that actually can decrease the value of resistance as well. Or it could be the fact that it isn't on the ring final circuit, and the only way to work out whether it isn't on the ring final circuit and they're a spur from it is also to take that cover off. So we'll do that next. We can clearly see there it was spurred from the ring final circuit, only having one line, one neutral and one circuit protective conductor. So we'd expect it to have the resistance of the readings that we've already got on the ring final circuit added to the value of the cable that got to the spurred outlet. Hence the reading was higher than the one we expected for all the outlets that are on that ring final circuit. Before we've completed stage 2 of the ring final circuit test, we must test all points on the circuit. So we've got a switch fuse connection unit here, and that feeds this lighting point here. So both of these will need to be checked as well at this stage. So we can clearly see by taking the front off, it is on the ring final circuit. However, we're going to have to go back to our leads in order to test it.
So with our leads connected and zeroed, we can connect the probes onto the termination points of the switched fused spur point. For this part, you may need 3 hands or an assist, but if you don't have a Gary, you can use the PR400 test probe, which has the test button on the probe. You can also set the MFT to be always on, so every time the tester detects a continuity, it will give you the reading. The reading was fine and within our 0.05 range. So now we head up to test at the lighting point. We first need to zero the adapter, remove the probes and plug it all in. Slightly odd though, as when Gary hit test, we got an open circuit until he realized that he had not operated the double pole switch. We get a higher reading, which is expected due to the additional cable length and smaller cross-sectional area going to the light fitting. So with all the points on the ring tested, we have our R1 plus RN reading, which is the highest reading taken from all the readings. But we don't actually record this on the model form, so why do it? Well, the reason is to ensure that there are no interconnections, spurs off spurs, or even perhaps a borrowed neutral. It also tells us that each point has a correct line to neutral termination, so polarity at the moment is looking good. This step is very similar to before, but this time we are testing between line and CPC. In a lot of installations, we would be testing between different size conductors, typically 2.5 and 1.5 twin and earth. Because the conductors aren't the same cross-sectional area, the parallel resistances are uneven, so the readings can vary slightly as you move around the ring. In theory, you'll see the values rise a little as you head towards the center of the circuit, then fall again as you return to the board. In most cases, the difference is tiny, maybe 0.05 ohms or about 6%. So often it goes unnoticed. Before we carry out the test, we are going to calculate our expected R1 plus R2 reading using the same formula as before. As the readings are exactly the same as the neutral readings, I am not expecting much difference, but let's do it anyway. So the formula is little r1 plus little r2 divided by 4, which will give us our expected r1 plus r2. The reading is the same as before at 0.11 ohms. This means our expected r1 plus r2 reading is just that. So let's get into it. As we can see, we make the cross connection between line and CPC, and then CPC and line, paying careful attention to the fact that the in of the line conductor is connected to the out of the CPC and the out of the line conductor is connected to the in of the CPC. So as before, we are going to follow the same sequence of testing of the sockets and the switched fused spur as we did during the R1 and RN test. So with the breakout lead connected and zeroed, we go to socket number 1. We start with a reading of 0.11 ohms. As before, we are testing every point to make sure the socket points is okay. Socket number 2 gives us a reading of 0.11 again at each point. Socket 3 gave us a reading of 0.11 at one point and at the other point 0.12. We would always take the highest reading when testing. However, as we have sockets yet to test, we may still get a higher reading. Socket number 4 gives us a reading of 0.11 and 0.1. Socket number 5 we know is a spur from when we tested our R1 plus RN, so we should expect a higher reading, as we are including the resistance of the cable for the spur as well as the rest of the ring. And we were correct, a reading of 0.26 ohms and 0.27 ohms at the other. So is the last point to test on the ring final circuit, the switched fused spur and lighting point, and there are a few things we need to do to get this right. We start with, as always when changing leads and probes, we zero them. We will now test the ring at the fuse connection unit. This can be a little awkward as you need to make sure you hold the probes on hard enough to get a good connection. An alternative, if you are on your own, would be to use the crocodile clip on the earth termination, again making sure you have a good connection. Testing at the lighting point means we get to use the adapter. However, as the adapter only makes the contact with line and neutral, we need to get to the ceiling rows to connect to the CPC. With the probe making contact we can test, and at this point we got a reading of 0.39 ohms, our highest reading on the ring. But we can't stop there, as we need to confirm polarity. I operate the switch and get an open circuit, exactly what we wanted, and proves that the switch is working, and also switching the line conductor. And as this is a switched fuse spur, we also need to test the operation of the fuse itself to ensure it will disconnect the line conductor. This also reassures us that the correct size fuse has been used for the expected load, and we get an open circuit. Let's put it all back together and take stock of our readings. In step 1, we tested our end-to-ends at the consumer unit. This we called our little R1, little RN, and little R2. We got a little R1 reading of 0.22, a little RN reading of 0.21, and a little R2 reading of 0.21. We then moved into step 2, which is testing our R1 plus RN. Before we dived into the test though, we calculated our expected R1 plus RN reading using the formula little r1 plus little rn divided by 4, and this gave us an expected reading of 0.11. We cross-connected our conductors at the consumer unit by connecting the line in with the neutral out and the neutral in with the line out. We then tested the R1 plus Rn at each socket point, and our highest reading was 0.28, which was taken from the lighting point. Our final step is step 3. We calculated our expected R1 plus R2, which was the same as our R1 plus Rn at 0.11. We cross-connect the same as before with the line in, connected to the CPC out, and the CPC in connected to the line out. We can now move between all the sockets as before, testing the R1 plus R2, and this time our highest reading was at the lighting point. The reading of 0.39 is the reading we will record on our schedule of test results.
Before you get uber excited and move on to another circuit, remember you can leave this ready for its insulation resistance test by leaving all switches in the on position, and that includes these ones in on the front of the sockets. So the test gets actually all the way to the front of the outlet itself. We've already left the fuse connection unit on, but remember, no loads in circuit. Make sure the lamp's out and nothing is plugged in before you leave this circuit.
Big thanks to Test Rigs UK Limited and Niglon for providing this training rig. I've left links in the description if you want to find out more about Test Rigs UK Limited and Niglon. Thanks as well to Test Instrument Solutions for sending us the MFT Pro. If you have a question, then get it into the comments or email me directly at willittrip@efix.co.uk. And if you want to dive deeper into carrying out insulation resistance tests, then watch this video right here.